Welcome to all in my YouTube channel. In this video, I am trying to explain the basic concept related to fluid mechanics, specific few law related to pressure, hydrostatic pressures and Pascal law, etc. This you can see this figure, and this is the application of Pascal law, where we are lifting the large weight of vehicle just by applying a smaller force. We also know hydrostatic law, pressure at the same level is equal in all directions. That means pressure at a point 1 is equal to pressure at a point 2, and we can write pressure, that means force per unit area, that means A1 is equal to pressure force F2 upon area A2. That means force F2 is F1 into A2 by A1. That means just by increasing the increasing the area ratio, we can lift the very large weight by using a smaller force. That is the application of Pascal law for lifting a large weight of vehicle. Now we are trying to explain the few basic question related to this concept. Let's suppose that this is another example. The pressure is measured by using a manometer. Manometer is nothing but it is a device which is used to measure a pressure. Let's suppose that a gas flowing in a pipeline and tank, and this pressure is measured by using a U-tube manometer. Initially, this U-tube manometer is like this, and in this we are filling. Initially both ends are open, and in which we are filling a fluid, either it may be a water or mercury, depending on the pressure requirement. Mercury is preferred when we are trying to measure a very large pressure in a flowing pipe or chamber. For this we can write the hydrostatic law by using, let's suppose that if PS is the gas pressure, so we can write the equation PS, and we are assuming pressure is same at all point, and this is the very low pressure. That means PS is equal to P1 is equal to pressure P2. But let's suppose that this is open to the atmosphere, and this pressure is the atmospheric pressure. So we can write, let's suppose that this fluid is a mercury, so we can write the equation P2 is equal to P atmosphere plus rho GH, rho that is the mercury, and G into height, that is the H. Using this equation we can solve another numerical related to this topic. This is a very interesting numerical asked in a question. Let's suppose that pressure of a steam flowing in a pipeline is measured with mercury manometer. That means a manometer is initially filled with a mercury, as shown in figure 1. Suppose that initially this is a U-tube manometer mercury. Initially mercury manometer is like this. I am trying to draw the figure, and this is filled with a mercury. Initially this is filled with a mercury, that is mercury, and a pipeline, steam pipeline is like this. steam pipeline is like this. But when we are not filled with connected with these two in this pipeline, this steam pipeline and mercury manometer, both are at the atmospheric pressure. So initially this will be at the atmospheric pressure and open to the atmosphere, that is the atmospheric pressure, that is the P naught. And mercury level initially both the right and both the side of tube are having the same mercury level. But when we connected to this pipe, first we connect to this pipe, steam pipeline. Let's suppose that we are connecting these two pipeline. Steam is flowing here, steam यहाँ flowing here, but few steam will condensate to the water. In a question, that means some steam condense into the water. Steam condense into a water. Let's suppose that this height and this condensed height is given, that is the water H2, and its height, let's suppose that 3 centimeter, its height 3 centimeter, and this portion is a mercury, and this portion is a mercury, and this height up to this point from this level is seen in a figure, that is 50 centimeter. Estimate the steam pressure in kilopascal and take the density of mercury 13.6 into 10 to the power 3 and density of water this, and barometer reading is 76.1 centimeter mercury, and acceleration due to gravity is this. This is the very interesting question, and we know first we will find the atmospheric pressure. P naught. It is not directly given. It is give relation to the with mercury manometer, and pressure P naught is equal to rho, density of mercury rho, and G and H and this height H1 is given. This height H1 is given in centimeter, so we will convert in meter. Density of mercury, that is 13.6 into 10 to the power 3, and G is the 9.806, and height, that means H1 76.1 in centimeter. I convert in meter, and after solving this we will find the pressure 101.36 approximately in kilopascal. Then we will apply the hydrostatic law for this figure, hydrostatic law. So writing the equation for this figure, and move from, when we moving in the downward direction taking pressure as a positive, and moving in the upward direction taking pressure as a negative. So applying the equation, I am trying to write the equation here. First, pressure of steam, let's suppose that pressure of steam is P, and moving in the downward direction up to this point is the same pressure, and we are assuming neglecting the gravity effect if not given in a question, plus applying plus for water, that means density of water rho G, and height, that is the, let's suppose that this height of the water is 3 centimeter, so that means 3 centimeter, and in meter we will divide it by 100. And now we are at this location. After this this is the same fluid, that is mercury. When moving in the downward direction, it will be taking as a positive, and in the upward direction we are taking as a negative, and both are equal, it will cancel out. So we will jump from 1 to 2 directly. Once it move from 1 to 2 directly, and moving in the upward direction 2, because in the downward direction and upward direction is same rho value, and it will be cancel out. Now try to write the equation for upward direction from point 2. We are taking minus sign for upward direction, and this fluid is the mercury. This fluid is mercury up to the point 2, that is rho mercury, and G and height, that is 50 centimeter, that means 50 upon 100 when converting in meter, and up to this point, and again this is the atmospheric pressure is equal to P atmosphere. After solving this equation, just put, that means pressure P plus density of water is given in a, that is 1000, that means 10 to the power 3, and G given in a question 9.806 into 0.03 minus density of mercury 13.6 into 10 to the power 3 into G 9.806 into 0.5 is equal to this pressure, that is the atmospheric pressure. We are already find this pressure, atmospheric pressure value, that means 101.36 kilopascal, that is the kilopascal. After solving this equation, that means pressure P plus, we are changing the whole value in a Pascal, but converting value in a kilopascal divided by 1000. So we will common multiply these two terms, and we will find 9.806 into 0.03 minus 13.6 into 9.806 into 0.5 is equal to 101.36, and both value, this side is also in a kilopascal and this value is also in a kilopascal. So just solve this equation, pressure P plus, after solving of these two pressures, we will find, and solving these two, we will find a total, that means pressure, find the total, that means pressure P is equal to 166.7466 and value in kilopascal. This is your solution.